Alright guys, so for our first structure here, we're going to be using the banner against the lamppost. With this structure, we have two pin support reactions. It's set up and designed this way so that way if there's any external forces like weather or gravity, it can maintain its static position. The banner will also maintain its position if creatures like the squirrel are going to be swinging around on it, right?
So for this object, we'll be looking at the inner part of this hole puncher where there's a base, a pin, and a lever. So the reason why the lever is pretty longer than usual hole punchers is because if we have an external force, it will be easier to use, whereas if it was shorter, say it was up to here, it would be harder to press. So a longer lever equals a greater moment.
This structure has 4 support reactions, all acting in the Y, none in the X, so that it can allow translation. The significance of the rotors having a force in the Y is so that it can maintain static motion, and so when any weight is applied to it, it stays right where it is and no translation in the Y. So the reason it was designed this way is so that it can be translated in the X. That way it is easier to move around along.
So, in this structure here, as you can see, it's being held by a string. It's a little paper snowflake being held by a string. The cool thing about this structure is it gives it that liveliness with the motion here, the rotating motion. The forces being applied here is actually tension force from the string and an X and Y force being applied here, the support reaction. So at the support reaction, it makes it so it can't translate in the X or Y direction, but because of the string, it allows it to move and circle here. The only way that we can actually get the snowflake to translate in the X or Y direction is if we actually apply a force. But again, at the point, it causes more of a rotation rather than like an actual translation.
Okay. Hello everyone, I did a bridge as one of the free body diagrams for this project. So this bridge has 2 support reactions going on in the Y direction, AY and BY. And I was standing in the center of this bridge, ideally, and with my weight right here, we're assuming 130 pounds, and the weight of the bridge, which is estimated at 2,000 pounds, we combined that into one uniform weight of 2,130 pounds. Now, I estimated this bridge to be about 9 meters long, and so the center point of that bridge is 4.5 meters. Now, to find the support reactions that are acting on the bridge, I created a moment, and as you can see, there's no forces in the X direction. So, back to the moment. I try to find, since both of these, since there's a pivot at both point A and B, there's moments being caused at both those points. So I found the moment acting at A. So as you can see, since there's no, since the distance is 0 at AY, we can cancel that off. So we have these 2 forces left that are perpendicular to the distance. The first one, which is the force of gravity acting on the weight of the bridge and myself, is calculated right here. 4.5 meters, which is the halfway point of the bridge, times the distance of the entire uniform weight of like the bridge and me. Plus, now the force of the support reaction times that distance, which is 9 meters. Now, if we solve for, we add everything up and we calculate for B, it turns out to be 1,065 newtons. Now, to find AY, we know that now I try to find everything in the Y direction. So we already know what BY is, so we can substitute for that. We already know the uniform weight of the bridge and myself. Now we can solve for AY, which ends up being the same thing as AY and BY, which I predicted to happen because since I'm standing in the center of the bridge, both the forces of these, the force of the support reaction should be the same since I'm standing right in the center. Thank you.
Alright guys, so in this system behind me, we have a truss system with 4 different support reactions. So we have one here, one there, one here, and one here as well, right? They're all pins that inhibit the actual truss from any rotational movement, keeps it in a static position. There are 2 acting members in this truss right here, and unfortunately because we don't have any numbers to calculate, we can't really determine whether at each one of these points if there's a compressive force or a tension force being applied. So the cool thing about this truss being here and why it's so important that it's set up the way that it is because in this Smith machine system here, we have a vertical piece here and we have a vertical piece here, okay? What that does is it inhibits the actual bench when you're using it. You know, you're pressing that Y direction. If you were to set up a Cartesian graph right here, you'd have that Y and X direction. It inhibits it from moving in that X direction. Now, why that's important with the truss being there, if the truss weren't there, it would cause these 2 vertical pieces to tilt, because obviously when you're working that muscle, you're incorporating a lot of stability, and it would allow the actual bar to move in not only the Y direction, but also in the X direction, which would essentially cause this whole thing to collapse and probably hurt or potentially kill someone. So yeah, it's kind of important.